A huge thanks to Brian for sponsoring this video. Fellow mathematicians, welcome back to another video. I am still pretty damn ill, but I can finally talk once again without sounding like a 10-year-old Minecraft player. By the way, have you checked out StemMage.eu in the last time? If you haven't done so already, make sure to check it out. We got some new products and more products to come in the next time. So today, improvised session, and because my throat is still hurting, I've got some tea with me. And since it already hurts, I felt like punishing myself more with this integral, this generalized one. The integral of the quotient of ax squared plus bx plus c and dx squared plus ex plus f. It's going to be terrible. It's going to be seriously terrible. Yeah, someone sent this to me via email because the person thought, well, why not punish Papa Flammy a tiny little bit? Yeah, and we are going to do this improvised session. Let's see if we can do it. I don't think it's a matter of being able to do it, but a matter of just making it to the end. This is going to be a long video, I suppose. By the way, if you're not familiar with integration yet, why not check out the calculus course over on Brian. More information at the end of the video. And now we are going to dive right in. So, first thing I'm going to do is I'm going to factor out a divided by d. Reason for that is that we are going to get monic polynomials in the numerator and the denominator. This is just going to make completing the square easier. So meaning this is a divided by d times the integral of x squared. If we factor out a up here, we are going to get plus b divided by a, let's call it px, and c divided by a is q plus q, divided by x squared. Then we get e divided by d, which we are going to call r. X, I don't want to write everything out, we are going to make a note at the side, and f divided by d is going to be rs. Yeah, s, integrate with respect to x, with, okay, let's say p is equal to b divided by a, q is equal to c divided by a, r is equal to e divided by d. Let's just get an overview, and s is equal to f divided by the d. Okay, yeah, and now I think we should just complete the square. Doesn't make sense to complete the square in the numerator. I don't think so. If we were to complete the square in the numerator, no, this wouldn't make any sense, I think, because even though if we break it up, and using the linearity of the integral and the summation in the numerator, turn this into two fractions. Even if we introduce a substitution, we're going to get problems with the numerator. So we are going to leave the numerator how it is. I hope you know what I mean here. And we are just going to complete the square on the denominator. So a divided by d of the integral x squared plus px plus q divided by, okay, so if we were to complete the square on x squared plus rx plus s, so the s really doesn't matter right now. What we are missing is a 2 here, so r over 2, meaning what we still need to add and subtract is r squared divided by 4, and we need to subtract it. Yes, exactly. Meaning we are going to get this part here at the front is x plus r divided by 2, but the whole thing squared. X plus r divided by 2. No, r divided by 2, not r squared. Squared. And then minus r squared over 4 plus s. Integrate with respect to x. Okay. For simplification purposes, we are going to call this part here so r squared, no, s minus r squared divided by 4. We are going to call this thing as t. Okay, t, because t comes after s. So if we were to break this up into 3 integrals respectively, we are going to get a divided by d integral of x squared divided by, now this right here is x plus r over 2 squared plus t dx and all the other ones. So plus a divided by d, integral of, so we got a p at the front, so we can bring it to the front, a times p. And now we get x divided by the same denominator once again, so x plus r over 2 squared plus t dx. And last but not least, plus, so we can bring the q to the front, a times q divided by the d, integral of dx divided by x plus r over 2 whole thing squared plus t. Okay, this is where we are at the moment. It actually doesn't look that bad, to be honest. Also some restrictions on all of our constants. The only restriction that I think applies here is that not all of the constants are equal to 0, right? So we want to have them non-zero all at the same time, at least for the denominator. We are going to see which restrictions apply once we get the antiderivative. Okay, now obviously we are going to introduce the substitution. Let, and the substitution includes obviously our part in the denominator here. Let x plus r over 2 be equal to, after t comes u. I don't like to use u substitution, but we are going to do this for the memes. That means that dx is equal to du. Obviously, meaning where we are at the moment is that all of this shit is equal to a divided by d, integral of. So x is nothing other than u minus r over 2. So u minus r over 2 squared divided by, oh goodness, this is terrible, because now we are going to get 3 more integrals out of this, and here we are going to get 2 more integrals. So we have to deal with 6 integrals overall, but I think the antiderivatives are going to be similar for at least 2 pairs of these, right? Should be, if I think about it in a polynomial kind of way. So u minus r squared, no, u minus r, but the whole thing squared divided by u squared plus t dt, and then plus a times p divided by d, integral of, okay, x is u minus r over 2 divided by u squared plus t dt, and then plus, yeah, we still need to introduce substitution. Why am I writing t all the time? Why did I do this? No. Oh yeah, because of the t here. That was weird. I need to use u, obviously. A times q divided by the d, integral of, my integral signs are looking kind of thick, mate. Thick. Yeah, they are looking pretty thick today. They are very, very formvoll-ended, as you would say in German. So now we get du divided by u squared plus t. Okay, awesome. Let us break all of these up numerator-wise, and then we can introduce some more substitutions. We can get terms which are like the same, okay, using the distributive property in the real numbers. So we just need to take into consideration that u minus r over 2 squared is the same as u squared minus 2 times r, so r times u plus r squared over 4. Okay, giving us overall that we end up with 6 integrals overall. So on the one hand we get a divided by d, integral of, so with the u squared part now, so u squared divided by u squared plus t du. Next up we are going to get plus. So negative r is a constant, we can bring it to the front with respect to the integration, so we are going to get negative a times r divided by d, integral of u divided by u squared plus t du. Next up, plus r squared over 4. We can bring this r squared over 4 to the front, so plus a times r squared over 4 times the d, integral of, and now we get du divided by u squared plus t. Okay, those are the first three. Let's get a nice overview. Let's write everything out very nicely such that we don't make any mistakes in the process. So plus a times p divided by the d, and then integral of, at first we get u divided by u squared plus t du. Next up we are going to get negative r over 2. We can bring this to the front once again. So negative a times p times r divided by 2d integral of du divided by u squared plus t. And last but not least plus a times q divided by d integral of du divided by u squared plus t. Those are the 6 integrals, and now let's see which are likewise, okay, which have likewise terms. So this part right here is completely standalone. We don't have other u squared polynomial in the numerator. So let us write this out. So this is just a times d, a divided by d, integral of u squared divided by u squared plus t du. Okay. Now next up, let's search for the monic polynomial in the numerator. So this is this part right here with a negative sign at the front and the coefficients, and this one. So we get, okay, let's see, let's try to just factor everything out that is nicely. So we get a divided by d as a term which all of these have in common. So plus a divided by d, and what we get in parentheses is negative r, so p minus r, times the integral of u divided by u squared plus t du. And those are all the remaining ones, okay? This and this and this. So a divided by d is a term which all of these have in common, but nothing else. Yes. So plus a divided by d. In parentheses goes r squared over 4. R squared over 4, this is this part. Minus PR divided by 2 plus Q, and then times the integral of du divided by u squared plus t. Okay, I think we sorted everything out very nicely up until this point. Now we can get into finding out what the antiderivatives are. So for these two it's easy, because this is just a substitution obviously. So if we substitute u squared plus t, we are going to get something u du, okay? And then we get rid of the numerator. This right here is something that you should all be familiar with. We are using this extensively here on this channel at all times. Just a quick little reminder. If we have the integral of, okay, this is just a side note, integral of dx divided by x squared plus a squared in our case. This is going to give you as the antiderivative 1 divided by a times the inverse tangent of x divided by a plus some arbitrary constant c. But since we only have a t here, we are going to interpret this as the square root of t, but the whole thing squared. Okay, meaning what we have here is that this is by the identity that we have used a lot here on this channel. Okay, when I created the video back in the days, I told you, remember this. This is like the most important identity ever in integration. If we have the square root of t here instead of our a, we're going to get that this is 1 divided by the square root of t times the inverse tangent of in our case u, divided by the square root of t. Okay, so we are done with this part. That was easy. Now, as for the substitution here, let u squared plus t be equal to, after u comes v, u vw, yeah, meaning u divided by 2 du, no, 2 times u. 2 times u du is equal to dv, meaning u du is equal to dv over 2. Meaning if we introduce this substitution, we are going to get that this right here is, so here it is. So in the denominator, we are going to get just v. Then we are going to get dv over 2 is equal to u du. So dv here, and we get a 1/2 at the front. Meaning, as the antiderivative, what we get here is just 1/2 times the natural log of v. So we are done with this. And now for u squared over u squared plus t. Do we need a trig substitution here? I'm thinking if we just introduce u squared. Let me think for a second. This is actually rather ugly, right? Do we need partial fractions here? I'm thinking at the moment, but we can factorize this part nicely. I need to think about this for a second. Let's put a little note here. U squared plus t. That's probably something very easy, but I am staying on the Schlauch at the moment. I am standing on the hose. Let me see for a second. U squared divided by u squared plus t. Let u be equal to I'm just thinking. I'm taking some notes here. It's probably something very easy, but I don't have it in my head right now. For an elementary antiderivative, let u squared plus t. If this is equal to, no, this is rather ugly. Partial fractions doesn't work here either very nicely because of the plus t that we are having, so we can factorize it easily. Or can we? Can we or can we not? I'm thinking. Let u be equal to t times the sine of phi. Okay, that means that du is equal to t times the cosine of phi. Let me think for a second. Then we are going to get that would be stupid. Not sine, but it's just because of the plus t that we're having here. Tangent plus 1. No. Was a tangent squared plus 1. Tangent squared plus 1. This is sine squared divided by cosine squared. That's sine plus cosine is 1 over secant squared. Yeah, that is better. Tangent, meaning we are going to get secant squared of phi down here. Okay, that means if we were to plug this in, okay, this is just a side note. So u squared is t squared times the tangent squared of phi divided by, now we are going to get t squared. Oh, this sucks because of the t squared. We should have square root of t, right? So square root of t here. I'm terribly sorry. If we have square root of t, we are just going to get t here. This is better. Then we are going to get u is once again tangent squared plus t. We can factor out the t here. So t's are all going to cancel out. We are just going to get also we are going to have the square root of t times the secant squared of phi, meaning this is all just integral of tangent squared divided by tangent squared plus 1, square root of t to the front, secant squared, d phi, obviously. Tangent squared plus 1 is the same as secant squared, so this is going to cancel out, leaving us with square root of t times the integral of tangent squared. Integral of tangent squared. Integral of tangent squared. Isn't that way harder to do? No, integral of tangent squared should be fairly. So this is just square root of t times the integral of sin squared over the cosine squared d phi. This is 1 minus the cosine squared at the top. So this is 1 minus secant squared. No, this is secant squared minus 1. So we need to integrate secant squared. Oh, goodness. I hate integral identities like this. Some other calc student would probably say, hey, I know this immediately. But if you don't do this on a daily basis, it gets harder. So this is the integral. So square root of t times the integral of d phi. Secant squared. Oh yeah, integral of secant squared obviously is tangent. Yeah, that makes it easy. Plus, minus the square root of t times phi. Because this was the integral of d phi. And this right here is tangent of phi. Okay, so this settles it, I suppose. I hope this is actually the antiderivative. Yeah, there was a lot of struggling here from my side, but what can you do? Now we just need to find out what phi is. Oh yeah, you could have introduced substitution. This is going to give you, or just partial fraction decomposition, but never mind. I'm seeing this now. So tangent of phi is u divided by the square root of t. So this right here is just going to give you u minus, and phi is the same as the inverse tangent of u divided by the square root of t. Yeah, this is exactly the same identity as we had before. Okay, yeah, this just happens from time to time, but good, we got the solution here in an elementary fashion. So minus the square root of t times the inverse tangent of u divided by the square root of t, it seems. Okay, cool. And now we can write everything out. So gotta write it here once again. So this is u minus the square root of t times, I'm just checking if everything is right here, but square root of t, yeah, seems to be the case. If I'm mistaken, then it just is what it is, u divided by the square root of t. Okay, but what is u exactly? U is the same as x plus r over 2, because we need to bring everything back to x. So this right here is a divided by d times u. So x plus r over 2. Very slow, very slowly. We don't want to make any mistakes here. Minus a times the square root of t. We're going to plug t in later in the game. Divided by d times the inverse tangent of x plus r over 2 divided by the square root of t. This is the first part. Plus, now we are going to get a divided by d times p minus r. And we get a 1/2, so 2 times d and the natural log of v, where v is u squared plus t, but u squared is x plus r over 2 squared. So we are going to get x plus r over 2 squared plus t. And last but not least, we are going to get this very short expression here, plus a divided by d. Then we are going to get r squared divided by 4 minus pr divided by 2 plus q. And all of these terms, and now I don't have anything that I could clean the chalkboard with. This is why I'm using my other t-shirt that I got here. I really don't care. Do we need this anymore? No, we don't. And now we get 1 over the square root of t times the inverse tangent, and u was x plus r over 2 divided by the square root of t. This is where we are at the moment. It's everything with respect to x plus some arbitrary constant kappa. And all that we need to do now is substitute all of our other things back, such that we have with respect to a, b, c, d, e, f. Yeah, and that's it. So this is first expression. Also inverse tangent. Are they the same? Inverse tangent x plus r over 2. Yes, they are actually the same, meaning we can factor out the a divided by d once again. So let's start off with the first expression. So we get a divided by d times x plus, and r is the same as e divided by d. Okay, e divided by d. Cool. So the first part is done. Then we are going to get, I'm going to continue with this one right here, plus a divided by 2 times d, p minus r. P is b divided by a, and r, so negative e divided by d, times the natural log of, now we get x plus r over 2. R is e divided by d, so x plus e divided by 2d squared, plus, and t has been, t, I need to put a note here, t is equal to s minus r squared over 4, but r is e divided by d and s is f divided by d. Meaning this is f divided by d minus, and now we are going to get e squared divided by 4d squared. Well, also we have a common factor of 1 over d, but I don't give a shit about that right now. We are not going to factor this out at this point. This really doesn't matter. So f divided by d, we are just going to add t to it, so minus e squared divided by 4d squared. Okay, that's it for the logarithm. And now we are on the final leap. We need to bring those two together. So at first we are going to get plus a divided by d. Then we are going to get minus square root of t, definitely, but we also have this part. So we have, those are the first ones, and now we got r squared divided by 4. R is e divided by d, so e squared divided by 4d squared minus p is the same as b divided by a. So b and r is e divided by d, so be divided by 2ad. That's a freaking mess. Oh. That's a freaking mess, seriously. Plus, and q is c divided by a. That's it for that. Times 1 over the square root of t. Yes, those are the only instances where we get square roots of t, if I'm not mistaken. And t is the same as, oh yeah, we had t before actually. T was somewhere here, but we have written it out. Square root of t. No, where were we? 1 over square root of t. So 1 divided by, and square root of t is the square root of f divided by d minus e squared divided by 4d squared. Okay. That was the square root of t. And then minus the square root of t. So minus the square root of the same thing that we got here. F divided by d minus e squared divided by 4d squared. And all of this times, okay, this is the last part that we get here, times the inverse tangent of. Now we are going to get x plus r over 2, but r is e divided by d. Why is r so prominent here? This is ridiculous. So x plus e divided by 2d divided by the square root of t, and we know what the square root of t is. This is nothing other than the square root of f divided by d minus e squared divided by 4t squared plus some arbitrary constant kappa. Hey, and this settles it. This wasn't even half bad, to be honest, but it's such a huge mess, and you need to be really careful such that you drag all your constants with you at all times. Obviously, you can now factor out the a divided by d as a common factor on all of these. Are there any restrictions? Obviously, d must not be equal to 0, because otherwise we would divide by d. Other than that, we also don't want t to be equal to 0. Okay, this is something that we don't want t to be equal to 0, so you need to place some restrictions here on all of these. So f times 4d squared must not be equal to e squared plus times d, obviously. This is also another restrictions. We don't want all of this to be equal to 0, obviously. This is something that we don't want. So I think we can get all of this out of the way if we just say that not all of the constants that we have here are at the same time equal to 0. So you can place some restrictions on it. But other than that, there was a lot of fun. Especially this integral, because I struggled a tiny little bit, but I think I got it done after all. I'm going to check with Wolfram Alpha, but I don't think that Wolfram Alpha can compute the original integral and spit me out a correct solution just because of all the constants here. But I can give it a shot, and if I can find the antiderivative in Wolfram Alpha, it's going to be here. But someone can please make sure to check if this is actually the case. The best way to check if this right here is actually the antiderivative is to differentiate it. But this is for another video. And I hope you have enjoyed what you have seen today. My throat actually feels way better at this point, and I can create videos once again. If it weren't for the cold, I wouldn't have I would have created more videos before. But yeah, that was a lot of fun. And if you're interested in more mathematics like this, calculus, integration, differentiation, then I invite you to try out the contents of today's sponsor, Brilliant, who I kind of to sponsor yet another video here on this channel. Now that was a very cool challenge, and you know what I'm going to do next? I'm going to go over to a graphics calculator and see how the integral is going to behave here, or just a function in and of itself. And Brilliant actually does the same thing on their website. Their website shines with interactive courses. If you are interested in finding out how a graph is going to behave under the influence of parameters, for example, then Brilliant might be the perfect fit for you. Especially in the calculus section, you are going to find a lot of graphs, interactive learning content that you can play around with firsthand, giving you a better understanding of the underlying concepts in those courses, be it the mathematics that we did today, physics, chemistry, or everything else that you can think about in the STEM field. Brilliant definitely got you covered with their over 60 interactive courses in all topics STEM. And some of my favorites include the geometry courses, also the linear algebra section, the courses on complex numbers, and also the calculus sections. The calculus sections is where they put a lot of emphasis on, just because American students have to go through a lot of calculus by themselves. And it's actually good that they do so, because a lot of the understanding for the concepts in calculus can be learned by just doing something with graphics, just trying to understand how a derivative is going to behave, what a derivative actually means in terms of the tangent line going along a function, for example. And this is what they are going to teach you over on their website. So if you are interested, if this feels like it's something for you, then definitely make sure to check out the link at the top of the description, brilliant.org/FlammableMaths. With it, you're going to get free access to a big portion of Brilliant already, but more importantly, the first 200 people to actually make use of the link get 20% of an annual premium subscription, which is a great deal considering how much content they have available on their website already, and how easily you are going to learn something new every day. They also got an app, such that you can walk around and learn something on the go. So definitely make sure to check it out and support the channel this way. And if you did enjoy what I have done today, then why not subscribe to the channel? Support the channel by checking out WAC, pre-register for the game, and also check out stemmerge.eu, as mentioned before at the start of the video. And I hope everything was correct that I have done here today. There was one of the longer improvised sessions, and up until the next video, I wish you guys a flammable day. Ciao!